Hello, and welcome to Astronomy 100. In this video, what we're going to do is wrap up the topic of at least the organization of the sky by concentrating on a really fundamentally important idea, and that is the concept of creating maps of the sky. Now, if you think about the surface of the Earth, a map of the surface of the Earth is of critical importance, especially in our modern world, when we have GPS units built into our phones. The ability to know where you're going by some sort of a device to tell you that is a very convenient thing, but of course it's relying on very accurate maps of the surface of the Earth. And creating maps of the surface of the Earth is very important when it came to the exploration of the Earth, because it helps you obviously know where you have been, where you are, and where you are going. Now, when it comes to astronomy, it's very similar, but for a slightly different way. So let's get started. I'll show you what I mean. Now, when we create maps of the sky, what we're really trying to do is solve one particular problem, among others, but one particular problem, and that is, how do we actually see or find things that we don't see? So in other words, we have to locate objects that are in the sky that are not necessarily visible to our eyes. So the key concepts that we're going to address in this video are how astronomers need a way to, of course, locate objects that are invisible to the naked eye. The example I want to give here, this galaxy, this is NGC 1300. Beautiful galaxy, and it's very much like the Milky Way galaxy, the one that we belong to, in its shape and in its size. More about that later in the semester. But this galaxy, as pretty as it is to see, is not visible to the naked eye. You could go outside and look up and look right at it, and you won't see it because it's too faint for us to see with our eyes. So how do we aim a telescope at the right place to be able to take a picture of something we can't see? So astronomers spend the majority of their time pointing their telescopes at parts of the sky that look blank, look like there's nothing there, but once they take their picture, it exposes and shows this beautiful galaxy. So the way that we have to do that is to create maps. You don't point the telescope at the object you want to see by looking at it and pointing at it. You actually look or point the telescope at the object you want to find by pointing to a coordinate. And so each object in the sky has a specific coordinate that allows you to point the telescope. We'll talk more about that in a minute. The other thing is the side benefits of this. You will also be able to figure out the universe and the overall map of the universe itself by creating maps of the sky. So when you look at the objects of the sky and you pinpoint their location on a map, you are also pinpointing their location in the universe itself. So by creating maps of the sky, you are ultimately mapping out the universe itself. The last thing we're going to see is that where you are on Earth is going to also determine what you see in the sky. There are things we can't see from the northern hemisphere, and there are things we can't see from the southern hemisphere. So let's go ahead and get started. Now, the way that we create maps of the sky is almost exactly the same way that we map the surface of the Earth. And this requires you to remember a few things from your past education. And if this is kind of new to you, make sure you pay careful attention, because you need to know this before you can learn the astronomy that we're about to see. On the surface of the Earth, what we can do is we can create a map of the Earth by taking advantage of reference points. For instance, the normal spin of the Earth on its axis creates a north pole and a south pole. These two spots on the surface of the Earth are defined by the rotation of the Earth itself. Because the Earth spins in a particular way, these 2 points are the rotational axis of the Earth itself. The other one is the equator. The equator is a reference point, but it is halfway between the North Pole and the South Pole. That's what gives its definition of its location, is the halfway point between the North and South Pole. So these are 3 reference points: North Pole, South Pole, equator. Now what we can do is we can indicate 2 distinct directions of movement. One of those directions can be from the equator heading towards the poles. So the further and further away from the equator we get, the closer we get to the poles, we are changing our latitude. So latitude is going away from the equator towards the poles. And if you move along the equator, we call that longitude. So you'll notice the lines are drawn this way, and as we move along the equator, we are changing the longitude of your location. Now, the idea is when we combine each of these two different directions, combine them, you can pinpoint any place on Earth. So this particular place on Earth has a specific latitude, how far from the equator it is, and it has a specific longitude. And when you combine the latitude and the longitude, you pinpoint that spot. So what we simply need is a set of numbers. There's a set of numbers for latitude. It goes from 0 degrees being at the equator to 90 degrees being at the North Pole to 90 degrees south being at the South Pole. And in longitude, it is the number of degrees all the way from 0 to 360 all the way around. So there's a latitude number and a longitude number that pinpoints every place on Earth. If you go to those two numbers, you will go to this location on Earth. Now this works really well. So in astronomy, we do something very similar, but it invokes an idea that needs a little bit of explaining. When you go outside and look at the sky, it looks as if there's a giant sphere surrounding the Earth and that all the stars are attached to that sphere. It's just an illusion. It's not real, but it looks that way. But if you go back thousands of years, the ancient Greeks actually believed in this celestial sphere. The celestial sphere was this surrounding sphere that had the Earth at the center, and all the stars were attached to it. They believed the celestial sphere is what held up the stars. And when you watch the stars move across the sky, you're actually seeing the celestial sphere move. Now, in reality, it doesn't exist. But if we pretend that it exists, what you'll notice is the celestial sphere is very much like the sphere of the surface of the Earth. And so we can use a coordinate system on the celestial sphere that is very similar to the coordinate system we use on Earth. So watch how these two come together. When it comes to the celestial sphere, we take the Earth reference points and we project them into the sky. So the North Pole of the Earth projects onto the celestial sphere to create the North Celestial Pole. So the sky has a North Pole to it. The South Pole of the Earth is projected onto the sky to create a South Celestial Pole. So if you were standing at the South Pole and you look straight overhead, you're looking at the South Celestial Pole. If you're on the North Pole of the Earth and you look straight overhead, you're looking at the North Celestial Pole. Take the equator of the Earth and simply project that onto the celestial sphere, and you get the celestial equator. So notice the sky has the exact same 3 reference points, just like the surface of the Earth. Now what we do next is we do almost the same thing. What we do is we use a coordinate system on the sky that is very analogous or just like what we do on Earth. On Earth, you move away from the equator towards the pole, you're moving in what's called latitude. But on the sky, when you move from the celestial equator towards the North Celestial Pole, you are actually moving in what's called declination. So declination is the same thing as the concept of latitude. And on Earth, when you move around the equator, you are changing your longitude. But on the sky, when you're moving around the celestial equator, it is called right ascension. So right ascension is like longitude on Earth, and declination is like latitude on Earth. So every single object, let's pretend that this is the object on the sky that you want to look at. This object has a particular right ascension, and it has a particular declination. Each of those is a number. So a number that represents right ascension will take you to there, and a number that represents declination will take you to there. And when you put those two together, you have found that point on the sky, And if that's where your object is located at that point, then you have found the object. So an astronomer, when an astronomer is looking for the objects they're going to photograph or study, they actually on a computer type in two numbers. They type in a right ascension number, they type in a declination number, and then the computer tells the telescope to move to that coordinate, and then of course that's where their object is. So as long as every single part of the sky has a specific right ascension and declination number, then we can now map the entire sky. Just like on Earth, every single place on Earth has a certain longitude and latitude, and you can now create a map of the entire surface of the Earth. Same idea, but it requires you to make sure you understand what longitude and latitude are because they're projected into the sky, and then of course it requires you to learn the new terminology. Now the last part of this is what you see in the sky depends on where you live. So let me show you what I mean by that. Let's say that you're at the North Pole. So this person, this imaginary person is at the North Pole. Now obviously they're quite tall. You're not normally 1,000 miles tall, but I had to make them big enough for you to see. So let's say that you're standing right at the North Pole of the Earth. This blue line is your horizon. So if you're at the North Pole, you cannot see around the curvature of the Earth. So from the North Pole, anything above the blue line is visible, but anything below the blue line you can't see. So this person's view of the universe from the North Pole is everything above this blue line. They get to see everything up here. Now, the problem though is the Earth turns on its axis, going around and around and around. And so from the North Pole, because of the way the Earth turns, you will never see anything below the blue line. You are perpetually going to see everything above the blue line, always in your sky, never rises, never sets, always in the sky, and there's half of the universe you will never see. You get to see one half of the universe. Now the person at the South Pole, same idea. They are on the rotation axis of the Earth, and this is their horizon line. They can't see anything right here. They can only see everything that's down here because of their location. And so they get to see half of the universe, and it's a half of the universe that the people at the North Pole don't get to see. So what you see from the South Pole is half of the universe, and what you see from the North Pole is the other half of the universe. So where on Earth would you have to go to see both halves or all of the universe? Well, you'd have to go to the equator. So if you're on the equator of the Earth, the rotation of the Earth now goes around like this. And so even though at any given moment, you can only see what's above the blue line from your location, over the course of a year, as the Earth spins on its axis and slowly works its way around the sun, it will make it so that you eventually get to see everything. You'll be able to see everything over here, and then everything over here, and everything over here. So at the equator, it's the only place on Earth that you get to see the entire universe. And this is where most of the big telescopes of the world are located. When an astronomer wants to build a very large telescope, they're going to want to build it in a place where you can see the entire universe because you want to try to study all objects. Now that's not always possible. For instance, in San Diego, here's where San Diego is. In San Diego, we get to see a big chunk of the universe, right? If we take this and spin it over to this side, the blue line would be like this. And so we end up getting to see everything from here all the way over here down to here. There's a portion down here that we can't see from San Diego because of our location and the turning of the Earth. But one of the biggest telescopes of the world, what used to be the biggest telescope in the world, the Palomar Observatory 200-inch telescope, is located in San Diego. And so sometimes we put a telescope in a convenient place that's not necessarily at the equator. We always try to get as close as possible, but there are some things from San Diego we can't see. So some objects in our universe are just not visible from San Diego, but we're fairly close. We're about 32 degrees north of the equator, so we end up getting to see just about many of, at least let's put it this way, many of the important objects, but there's some that we can't. So it is not a coincidence that you'll notice that big telescopes or new modern telescopes are built in places that are very close to the equator. And some of these places are places like Hawaii. Hawaii is not at the equator exactly, but it's very close. And some of the biggest telescopes in the world are in Hawaii. And it's not a coincidence. It's because of its location and the ability to see the entire sky. So what you can see is that we need to create maps to pinpoint the locations of objects and also to find objects that are invisible to our eyes. But what we see of those mapped places of the sky are also going to depend on where we are on Earth and what we can see from that location and what we can't see from that location. So it just depends on where you are and what you see in the sky. So we're just about out of time. I hope you join me for the next video.